Hello everyone, my name is Alex Jankolski. I'm a Principal Solutions Architect in the Worldwide Specialist Organization, and today I'd like to share with you Amazon EKS support in SageMaker HyperPod. What is SageMaker HyperPod? It's a SageMaker service that provides purpose-built machine learning infrastructure with built-in resiliency features. Workloads on SageMaker HyperPod can be orchestrated either via Slurm or Kubernetes. And today we'll focus on the Kubernetes interface, which is provided by Amazon EKS, the Elastic Kubernetes Service. Even though this is a SageMaker service, customers can still access their underlying infrastructure using kubectl or SSH. A typical HyperPod cluster looks like this. The compute lives in a service account. And in addition to that, there's the customer account and an EKS cluster. The demo that I'd like to show you today has 4 separate instance groups in the compute cluster. One is a generic CPU group provided by M5 2x large instances. 2 is a G5 8x large node group, which has one EFA interface, one NVIDIA A10 GPU for each node. Then a node group with P5 instances, which has 32 EFA adapters and 8 NVIDIA H100 GPUs. And then finally, a Trainium 1 instance group. Each Trainium instance has 16 EFA adapters and 16 neuron devices. Each neuron device has 2 neuron cores, so there are a total of 32 neuron cores on each Trainium instance. And this instance group will basically have 64 neuron cores altogether. In the user or the customer VPC, we'll use the Amazon Elastic Container Registry. We'll have a shared FSX for Lustre volume, and we'll use Amazon CloudWatch Container Insights. The features of HyperPod are grouped around 3 experiences. First is the admin experience. This provides you the ability to create, update, delete clusters, access your clusters via kubectl, and if you need to, you can access the nodes via SSH. And the admin UI experience also includes access from the AWS console through the SageMaker UI. The resiliency feature includes deep health checks, health monitoring that's ongoing while the nodes are in service, and a job auto resume if the running jobs are interrupted due to hardware failure. Finally, the scientist experience is provided by HyperPod CLI, and it enables users who are not familiar with the Kubernetes API to have an easy interface to submit and manage their jobs on HyperPod clusters. Of course, we'll also cover observability features of HyperPod. One thing I wanted to note is that you can start from scratch and provision all of the resources that are necessary to create a HyperPod cluster. But if you already have a VPC and an existing EKS cluster, you can actually attach HyperPod compute to your existing infrastructure. And if you've already built things on top of the Kubernetes API, this would be an easy transition for you, because you can bring things like job submission, interfaces, queuing, or monitoring tools that run on top of the Kubernetes API, and they should work on HyperPod. To create a cluster, as I mentioned, first you need to create some basic resources in your VPC. And then I need to provision a EKS cluster. Some lifecycle scripts get pushed to an S3 bucket that help initialize nodes when they're about to join the cluster. And with this information, we create a HyperPod cluster configuration, which is displayed on the right. I want to point out here that in this example, we're configuring one instance group with P548 X large instances. We're saying that we want those to have deep health checks enabled by specifying this enable burn-in test setting. And node auto recovery is also configurable in this configuration file. So once we have the cluster configuration, we execute a create cluster command, and then the nodes get provisioned and a user can interact with them using kubectl. All of these steps are documented and provided to you in the workshop that we have released. This is a view of the workshop. As you can see here, it has everything from creating the cluster to running different examples on it, setting up observability, and testing resiliency features, as well as cleaning everything up at the end. So this is an end-to-end walkthrough for the entire process. One thing I want to point out is the sample cluster configuration file. As we discussed, there are settings which allow you to control the behavior of the resiliency features. If the deep health checks are disabled, then the health monitoring agent will still monitor your nodes, but the initialization time, we're not going to run all of these stress tests and connectivity tests. It will accelerate the time a new provision node is added to the cluster, but it will also trade off the deep health verification that happens prior to the node joining. If the deep health checks are enabled, they do take some time. Sometimes it can take up to a couple of hours for all of the checks to take place before a node joins in. So they're very, very extensive deep health checks that we're going to see in action during the demo. So to automate all of the steps that the workshop is walking you through, we have created this AWS Do HyperPod container project. This is an open source project that we'll share with you on the resources slide. And the purpose of it is to make it easy for you to get started and to interact with your HyperPod infrastructure without us asking you to install several things in your environment first. This project lets you run a build script, which builds a container for you that already has everything in it. And by everything, I mean all tools that we have found useful when interacting with Amazon EKS, as well as SageMaker HyperPod. That includes the HyperPod CLI, which provides scientists' experience. If you type just HyperPod inside that container shell that we just looked at, you'll see the help and the commands that are available are pretty self-explanatory. You can list your compute, and then you can start a job, manage your jobs, and see the logs of those jobs. On the right here is an example of how we run the HyperPod list clusters command, and it shows the different instance groups that we have in the cluster. So with this, let me switch over to one of my demo screens and show you the AWS Do HyperPod project. I have cloned it here already, and I've run the build script, so I've built the container. I've also executed the run.sh command, which started my container. And if I check my current status, I will see that the container is actually up and running. This gives me the ability to just exec in the container, which gives me a shell inside this AWS Do HyperPod container. The command that I just executed with each of these scripts gets printed out. So if you really wanted to type the long command, you could do that as well. But now that I'm inside this shell, I have scripts that allow me to configure a HyperPod cluster and then create it with just one command. And this supports both creating everything from scratch or attaching to an existing cluster. Let me just show the configuration real quick. And by the way, the environment config opens the project configuration, and you can switch between EKS and Slurm behavior for this container if you wanted to use this for Slurm as well. So showing the configuration of the cluster that I have built for this demonstration, I have these 4 node groups, G5, P5, Trainium 1N, and M5 instances. Each of them have 2 nodes, and my health checks they were enabled in the beginning, and then I switched it to disable the deep health checks so I can add new nodes quickly. And I have then updated the cluster. So currently my checks, deep health checks, are disabled, but if I switch that to true and ran the HyperPod update command, it will enable them. It's that easy. If I wanted to attach to an existing EKS cluster, then I just specify these settings here and run the cluster create command to attach to existing. I can demonstrate, for example, the HyperPod status command, and here is showing my cluster, and it is in service. A number of useful commands are available here. As I mentioned, the HyperPod CLI is already installed, but there is things like Node Viewer, which shows the cluster configuration, the nodes running on it, and how pods are distributed between the different nodes. We also have K9s, which is a tool many people use to kind of interact with their EKS cluster using this text user interface. There are a number of aliases, which you can see by typing the alias command, which saves a lot of typing. For example, I wouldn't be typing kubectl all the time. I'll just type K, and that will be equivalent. So I have already ran a few commands, and I'm going to split my screen here to show on the upper right corner, I've run the watch nodes command, or WN, and I am seeing the list of nodes I have in the cluster, as well as their instance types and their current health status. On the upper left here, I'm seeing the list of running pods in my default namespace, and here I'm just running K9s and looking at the different namespaces that are in the cluster. The Amazon CloudWatch namespace is created when you deploy the EKS CloudWatch Observability add-on, and it basically collects health and metrics utilization information from the cluster and publishes it on CloudWatch Container Insights. We'll see that later. The HyperPod namespace here has a number of health check pods. The ones that we see as completed are deep health checks that ran at initialization time. Their stress tests, their connectivity tests for the EFA adapters, very, very comprehensive. And then for each of the nodes, there is a health monitoring agent that is constantly screening for hardware and kernel level failures, which then can be remediated either by reboot or replacement of the node. So let's run an example of distributed training in this cluster. And since we have all of these node groups, we're going to run one training example on each node group. On the CPU instances, we're going to run an ImageNet CPU example. On the A10 GPU instances, we'll run the same example only on GPUs. Then on the H100s, on the P5 nodes, we're going to run a Llama 2 FSDP pre-training, and on the Neuron cores on the Trainium 1 nodes, we're going to run Llama 3 pre-training. So I have set up my cursor to broadcast what I type to all windows here. So this is the common part, and here I want to do ImageNet CPU. Here I want ImageNet GPU. Here I want FSDP, and here I want Llama 3 train. These first two examples are available in the AWS Do HyperPod project. The latter two are available in the Awesome Distributed Training project. We'll share all of these links in the resources slide at the end. But now I'm ready to basically, with one click, kick off 4 training jobs, and each of them will go to their respective compute resource on the HyperPod cluster, and we're going to see, I'll just get the list of pods here to see if everything is up and running. So now everything is up and running, and I'll use a command called kubetail or just KT as an alias. And on the first window, I'll monitor the CPUs here, the A10 GPUs for ImageNet. Here I'll do FSDP. So I'm just specifying a unique substring that grabs the pods that I'm interested in seeing. And then this one will be Llama 3. So now, with one click, I'm able to see an aggregated log of all of my relevant pods on each of the compute instance groups. On the CPUs, training has started. We can see that it's going kind of slow. On the A10 GPUs, training started. We can see it's going much faster than the CPUs. And then on the H100s, Llama 2 training is already started. On the Neuron cores, we're going through initialization, and then we're going to compile the graph of the model. Yeah, it says successfully compiled graph over here, and then training will start. So what are our nodes doing? It would be really interesting to see right now all of the compute and how the utilization is going. So we can do this from the command line, and I'll do that now. Later, we'll show also how to do this from Container Insights. For like immediate view into the utilization, we can use HTOP for the CPUs, NVTOP for the GPUs, and Neuron top for the neuron cores. I've set up this view here on my next demo screen. On the top line, we're running the htop command on both of these nodes. Example of this is included in the AWS Do HyperPod project. So we're seeing that the CPUs are utilized at close to 100%. And then on the next line here, we have the two GPUs. One of them has disconnected, but I can reconnect it here real quick. And to enlarge this screen, this is what we're looking at. The GPU utilization, single GPU on a G5 instance has high GPU utilization, and since ImageNet is a pretty small model, the memory utilization on that GPU is lower. Next line is the P5 instances, the 8 H100 GPUs. This looks like this. Our Llama 2 pre-training is going well, and we're utilizing our GPUs. And here's a visualization of the memory and GPU utilization as well. And finally, when the neuron job is started, we can also see utilization of all of the neuron devices. Each node has 16 neuron devices here, and each neuron device has 2 neuron cores. So in all, you have 32 neuron cores that are working in parallel on this pre-training of Llama 3. And we can drill down into each of the neuron cores and basically see the processes and the utilization that it has. So with this, let me dive a little deeper into resiliency. As I mentioned, the health monitoring agent is constantly looking for any errors to occur. And I'm going to use my CLI in the Do HyperPod project to inject a failure and simulate a failure in one of my G5 nodes and see what happens. So scripts for that are already provided in the deployment folder. So I have two ways of simulating that failure. One is this is a little bit of a hack. It actually injects a log line in the instance by running this script. And then the other way is just tagging the instance for reboot or replacement. But I'll do this one because it's more fun to inject a fault into the instance. So we'll inject a fault that requires a reboot to remediate. And I'll pick this G5 instance over here. And as soon as I run this, you will notice that the pod, a job was run that inserted this failure into the system log, and then the node was immediately marked as unschedulable pending reboot by the HyperPod service. And now the node is in reboot mode. The job that is running on it will, the pod that is running on it will fail. The job will go into a holding pattern while the node is rebooting. But then when the node becomes ready and schedulable again, the job will resume from the last saved checkpoint. This takes a little bit of time, about 10 minutes or so. So I've taken screenshots to show how this looks. They may be a little small, but here is the point where we have injected the fault, and then we have the worker pod error out, but the job continues to run. The node becomes not ready, reboots, becomes schedulable again, and the job is resumed by restarting that failed pod, and it continues to work from the last save checkpoint. Let's take a look at how this cluster can be visualized in the AWS console. I have a view of AWS SageMaker over here. So now you can, in the menu, drill down to HyperPod clusters and go to cluster management, and you'll see a list of your HyperPod clusters. When you drill down into your cluster, you will see its information, the nodes, their health status, and the worker groups that are part of this node, of this cluster. To observe the workloads that are running on this cluster, there are many ways. As we saw, you can do that from the command line. Also, you're able to just use a standard Prometheus Grafana stack. Instructions for that are provided in the workshop. And in my opinion, the best way to visualize the workloads in your cluster and utilization metrics is through CloudWatch Container Insights, which come out of the box with many default tiles that are useful but can be customized to your liking as well. So when you navigate to CloudWatch and Container Insights, then you're able to see kind of a graph of your clusters, and in the performance and summary tile right out of the box, you have HyperPod node health status. Then when you drill into the cluster of your choice at cluster, you can visualize metrics at all levels, but HyperPod specific metrics are included on the cluster and nodes level by default. As we can see here, since we're running a lot of training jobs, our utilization is high, both for CPUs, GPUs, and neuron cores. We have currently 7 healthy and 1 unhealthy nodes because we injected that failure, but this is in the process of auto recovery, so it will eventually get to 8 healthy nodes again. And on the node level, if we take a look, we have detailed, again, CPU, GPU utilization, disk utilization, including EFA, network utilization. This is important, how the interconnect between all of our nodes in our distributed training infrastructure is working. And finally, we have the HyperPod resiliency metrics as well included right here. So this all comes out of the box. You can build custom dashboards, but it is really, really convenient to just deploy the observability add-on and get all of this information right in your CloudWatch Container Insights. Next, I would like to go over some resources that might be helpful for you. First and foremost, the HyperPod EKS workshop is a resource that you could use either in your own account or as part of an AWS event or enablement series, or talk to your account team about setting up a dedicated event for you. This would give you all information about how to use and provision and manage your workloads on SageMaker HyperPod. The getting started quickly out of the box experience you get from the AWS Do HyperPod project is available from GitHub. Just clone the project, run the build and run scripts, and you're up and running. If you prefer, you could just pull the container from the public catalog on the public Elastic Container Registry Amazon hosts. So you don't even have to clone and build the project. And next, the SageMaker HyperPod CLI is also available on GitHub, and you're able to install that in any environment that you wish. The awesome distributed training project is a resource that provides examples, architectures, and tests both for Slurm and EKS-based clusters. The AWS Do Ray project is not HyperPod specific, but because it's built on top of EKS, it runs out of the box on SageMaker HyperPod with EKS support, and it enables you to create Ray clusters on EKS and run distributed training and inference jobs. There are examples for that provided in the project. And finally, the Awesome Inference project has several useful inference examples for EKS, including running NVIDIA NIMs. I'd like to wrap up by these three takeaways. First, SageMaker HyperPod provides purpose-built infrastructure for your ML and AI workloads. It has resilience capabilities which ensure that hardware failures are detected and resolved automatically on the customer's behalf. And you can orchestrate your jobs on SageMaker HyperPod using Slurm or EKS or the HyperPod CLI. It's a very open system, and it adjusts to what is most comfortable for you to make using AWS infrastructure easier and more productive for our customers. Last, I'd like to say thank you to all of my colleagues who worked on the SageMaker HyperPod service and made this possible. I also want to say thank you to our viewers. I hope you found this video useful, and I look forward to learning about all the amazing things you're going to build on AWS using SageMaker HyperPod.